47th lecture, and we are going to discuss the properties and synthesis of transfer parameters. In the last lecture, we had discussed some of the properties of transfer functions, and a summary is as follows. We showed that all transfer functions, we take several examples of transfer functions, and we showed that all transfer functions involve, besides the driving point parameters, that is z11, z22 or y11, y22, the transfer parameters z12 or y12. We have assumed the networks to be reciprocal, therefore, it is either z21 or z12, it does not matter, they are equal, they are identical. We showed that all transfer functions are real for S real. They are regular in right half plane. Does this mean something to you? Regular in right half plane means there are no poles in the right half plane. Regularity means absence of poles, no poles in the right half plane. All transfer functions are with no multiple poles on the j omega axis, because multiple poles on the j omega axis give rise to instability, and we are talking of passive stable reciprocal networks. In all transfer functions, the degree of the numerator cannot exceed the degree of the denominator by more than 1, whereas the reverse is not true, that is, the denominator may exceed the degree of the numerator by any number. Okay? All transfer functions are such that the magnitude is an even function and the angle is an odd function. This is where we ended the last lecture. All right. Today, yes.
So that means that a transfer function cannot have a multiple pole even at infinity?
It cannot have a multiple pole even at infinity. No, it cannot. It can have a simple pole at infinity. Okay, since all transfer functions involve z12 or y12, and in addition to the driving point parameters, that is z11, z22 or y11, y22, the properties of which you already know because they are DPIs, it suffices to consider the properties of z12 and y12. And there are several properties which are of interest to us at the moment. we shall discuss only those. One of the properties is that poles of z12 are also poles of z11 and z22 both. Okay, z11 and z22 both. But the reverse is not necessarily true. What we mean is that any pole of z12, if z12 s0 tends to infinity, this implies that z11 s0, z22 s0, both of them will tend to infinity. But the reverse is not necessarily true. That means if z11 has a pole, it is not necessarily shared by z12. If z22 has a pole, it is not necessarily shared by z12. The question at this point is, if z11 has a pole, does it have to be shared by z22? No. All right. It suffices to make a counter example.
What about z12?
What about if z11 has a pole, it does not necessarily have to be shared with z12. That is, the reverse is not necessarily true.
But also z22.
Also z22. z11 and z22 can have poles which are independent of each other and independent of z12. One example, one counter example will suffice to prove this.
The poles at the same point for z11 and z22.
That is what I was saying, that z11 poles and z22 poles can be independent of each other. They can also be independent of z12. But z12 cannot have a pole which is not shared by both z11 and z22. Agree? What I said is, the forward statement is correct, the reverse statement is not necessarily true. In other words, it is possible for z11 to have a pole which is not shared by either z12 or z22. Similarly, Z22 can have a pole which is not shared by Z11 or Z12. And a simple counter example.
But if both Z11 and Z22 have pole at certain point, then it is necessary to have the Z1 to have.
It is not necessary to have this belong to Z12 also.
Not
Not necessary. In addition, Z11 and Z22 themselves can have independent poles. They don't have to share a pole. Okay. A simple example would be this. Suppose we have a two-port network which has the parameters, let's say Z11 prime, Z12 prime and Z22 prime. Okay. Suppose we have a network like this. And then what we do is we supplement this with an impedance Z2 here and an impedance Z1 here. Okay. We supplement this with an impedance and call the total network as the unprimed network. That is, we call this as Z11, Z12 and Z22. Alright. There is a network inside which is a prime network, and then we supplement it with the help of two series impedances Z1 and Z2. Now you notice that Z11 is simply equal to Z11 prime plus Z1. Agree? Similarly, Z22 is Z22 prime plus Z2. And what about Z12? Same. Z12 prime. Alright. Therefore, the poles of Z1 are poles of Z11. Not necessarily, the poles of Z1 do not affect Z12. Isn't that right? The poles of Z1 do not affect Z12. Z12 is the same as the previous Z12 prime. Similarly, the poles of Z2 affects only Z22, not Z11 or Z12. And this simple example shows that Z11 can have a pole which does not belong to either of the other two parameters. Z22 can have a pole which does not belong to either Z11 or Z12. But any pole of Z12 must belong to Z11 as well as Z22.
So how do we prove that?
How do I prove that this pole also belongs to this? Okay, good question.
Excuse me, sir. Could
Yeah.
you please write clearly, sir? One of the
Oh, it's not clear, the writing? Oh, we'll give this up. Alright. How do I prove that any pole of Z12 also belongs to Z11 and Z22? Alright. Let's recall our node analysis. We have two current generators. Is this clear? Can you see this? Okay. We have two current generators at the two ports. We call this as node 1, this is node 2. There is some reference inside, some reference, and the voltages are V1 and V2. Okay. You recall that the node analysis gives you a nodal admittance matrix Yn multiplied by the nodal voltage vector Vn. This is equal to In. Alright. This is the node matrix equation, the nodal equation, nodal analysis equation. It can be put in this matrix form. You have self admittances and mutual admittances and so on and so forth. Alright. Is this okay? Where I have just two generators, I1 and I2. So In, for example, is equal to I1, I2, then 0, 0, 0, etc. 0. Alright. And what we wanted to find out is V1 and V2, that is these two voltages. I want to express in terms of I1 and I2. And you recall that this was I1 del 1 1 by del plus I2 del 1 2 by del, where del is the determinant of this matrix. Similarly, I have done this earlier. V2 is I1 del 2 1 by del plus I2 del 2 2 by del. Agree? So you can now identify what are your Z11, Z12. This is obviously Z11 and this is Z12, which is the same as Z21 because the network is reciprocal. Del 12 is equal to del 21 and this is equal to Z22. And you see that poles of all the functions should normally be the same because the poles are created by putting del equal to 0. Any value of s at which del equal to 0 is a pole. This pole should be shared by all the 4 parameters. Any pole of Z12 must also belong to Z11. Alright, but the reverse is not necessarily true, which is shown by this simple example that if there is an element in series at port 1, this affects only Z11, nothing else.
So, but for this case,
Yeah.
as he proved, if del is 0,
If del is 0,
for the pole for Z11, del should be 0.
correct.
So again, it implies Z1 to
So
Z1.
what I do is I add an element, another element Z1 in series with this. So all that it changes is that it becomes Z1 plus del 11 by del. So any pole of Z1 also is now a pole of the augmented network. It does not affect Z22 or Z12. Alright. So
del 11 can also have a pole.
del 11, then the whole thing is not a pole. Or del 11 can also have a pole at the same point.
At any other point, sir, the expression can.
That will be an independent pole. of
That will be an
another
independent pole.
sir.
So
That will be
that
another
again,
pole.
so del 1 2 can have a pole.
You see, what you are going to do ultimately is that del 11 and del both in general will be rational functions. And what you will do is you will make this into a polynomial divided by polynomial by clearing of inverse expressions like 1 by SC1 and so on. So the denominators of all these rational functions will be the same. Correct? And therefore the poles or the zeros of the denominator shall occur at the same point. Poles must in general be shared. On the other hand, there are exceptions with regard to Z11 and Z22 because we can add anything in series. It does not affect Z12. Alright, let's take a simple example. Let's have an inductor L1, a capacitor C1, and let's say an L2 and C2. C2. Okay, what are Z11, Z12, Z and Z22 of this structure? SL1 plus 1 over SC1. Z12, what is it equal to? 1 over SC1. And Z22 is 1 over SC1 plus, can someone tell me what this is?
SCL plus by S square CL.
SL2 divided by S squared C2L2 plus 1. Agreed? Which is equal to 1 over C2 S divided by S squared plus 1 over C2L2. I'm sorry, plus 1 over SC1. This we must ignore. We must not ignore. And if you notice that the pole at S equal to 0, which is the pole of Z12, is also present in Z11 and Z22. That is, this pole is shared by all the 3 parameters. On the other hand, the pole at infinity of Z11 is not shared by either Z12 or Z22. There is no pole at infinity of either of them. So this pole is as if a personal property of Z11. It is called a personal pole. You may call it a personal pole. Similarly, the pair of poles at plus minus j by square root C2L2 belongs only to Z22. It doesn't belong to Z11 and Z12. Alright? So the property is that any pole of Z12 must also belong to Z22 and Z11, but Z11 and Z22 can have poles which are personal to themselves. It doesn't have to be shared. Z12 is not in that privileged position. The transfer parameter poles must be shared by the other two parameters also. In a similar manner, you can show that if you take the y11, y22 and y12 parameters, you can show that all poles of y12 must also belong to y11 and y22. All poles of y12 must belong to y11 and y22 both, but the reverse statement is not necessarily true. That is, y11 can have a pole which is not shared with y22 or y12. Y22 can have a pole which is not necessarily shared by y11 as well as y12. And the counter example here is that if you add an admittance in parallel with port 1, if you add an admittance in parallel with port 1, y1, and an admittance y2 here, then y1 affects small y11 only, y2 affects small y22 only. It is exactly the dual of the previous case. In the previous case, we had used two impedances in series. Now there are two admittances in parallel. Y1 does not affect y22. Why not? Because in measuring y22 you have to short this. So y1 goes out of the picture. Okay. Now the third property that we shall be interested in is the special case of an LC two port. If a two port is LC, okay, then you know that Z11, Z22 and Y11 and Y22, they have a particular character. Can you pinpoint this character? What kind of rational function? Odd. All of them are odd. Odd rational functions. If the two port is LC, then all of them are odd rational functions. What can you say about Z12 and Y12? What can you say about Z12 and Y12? Can they be even, or can they be neither odd nor even? This requires a bit of investigation. Now, I cannot give you strict proof of this. This is beyond the scope of the class, but let me cite a very simple logic. Suppose we consider Z12. By definition, what is Z12? Z12 is, what is the definition? V2 by I1. V1 by I2. Okay, all right. I have a current generator I2 here, and V1, this has to be kept open circuited, and these elements are all LC. All right. So, under this condition, if I measure V1 by I2, this would be Z12. We are asking the question, what is there any special character that you can assign to Z12? Is it purely even? Is it purely odd? Or is it neither purely even nor purely odd? Okay, this is the question that I am asking. The logic that I am extending is the following, that if this is an LC network, any voltage in the LC network and any current in the LC network, any voltage and any current, they have to be 90 degrees out of phase in the steady state. Isn't that right? In other words, if I take Z12 j omega, this has to be purely imaginary, which means that real part of Z12 j omega must be equal to 0, which means now that Z12 of S, if it is purely imaginary for S equal to j omega, obviously Z12 of S must be purely odd. So, the property that we have come to the conclusion now is that for an LC2 port, all parameters, all z parameters and all y parameters must be purely odd. So, you add to this z12 and add to this y12. All of them must be odd rational functions. Could I explain it again? The argument that I gave was all voltages shall have to be 90° out of phase, because at a particular frequency, at a sinusoidal frequency in the steady state, all voltages must be 90° out of phase with all currents irrespective of where you measure it. And therefore, this ratio, if I take the real part, that must be 0. For s equal to j omega, it must be purely imaginary, either plus j times a constant or minus j times a constant, that is either plus 90 or minus 90. We cannot have a real part.
So isn't it obvious that since it cannot have, isn't it obvious?
What is obvious?
So since it's an LC,
It is not a driving point function. If it is a driving point function, it is obvious. It is a transfer parameter now, which means that at any point you measure the voltage. At any other point you measure the current. These two voltages and currents must be 90° out of phase. It cannot be anything otherwise. They cannot be in between because it is an LC network.
But when you say that the voltage and the current should be 90 degrees out of phase, shouldn't they be measured at the same point?
No, not necessarily. You can draw a phasor diagram with voltages and currents at different points. No
Then
problem.
it's possible for them to be in phase also, because current, inductor and
They cannot be in phase. No voltage and current can be in phase in an LC network.
So can we have an example?
You construct your example. You construct a counter example,
So, what about resonance?
not example.
it's in a case of resonance.
In the case of resonance, well, I was expecting this. If you have a voltage and current, this is a driving point function. Okay, if this is V and this is I, okay, then the impedance is 0, which means that the ratio of voltage to current is either 0 or infinity. In other words, at that point it has a pole. We are not talking of a pole or a 0. Okay, we are talking in general. If the function has a pole, well, all LC parameters have to have poles on the j omega axis only. Oh, is that obvious? That if the network is LC, that's an interesting point. Let's pause for a moment. If the network is LC, then all poles have to be on the j omega axis? Poles of all the parameters? Yes, because Z12 cannot have a pole which is not shared by Z11 and Z22 also. So Z12 poles must also be on the j omega axis. Okay, we are not talking of poles or zeros. We are talking of the ratio of frequency at which the ratio is neither pole nor a zero. At that point, the voltage and current measured anywhere in the network shall be 90° out of phase. And if you consider this a challenge, construct a counter example. All right, that I leave to you. The third point, that I third or fourth? It shall be the fourth point. Okay, the fourth point that I want to mention here is the following, and this I have to state without proof, because the proof is beyond the scope of this of this class. The fourth point is that if you have a set of parameters, let's say Z11, Z22, Z12, and suppose all of them have a pole at let's say some point s equal to s naught with residues. If there is a pole, there should be a residue, okay, with residues K11, K22 and K12. Alright. Then the statement of this property is that if the network is two element kind, that is, it is either LC or RC or RL. If the network is two element kind, that is, it's either LC or RC or RL, then the following property is true, that is K11 K22 minus K12 squared is greater than or equal to 0, and this is called the residue condition. As I said, I cannot prove this in this class, it is beyond the scope of this class, but I can definitely illustrate by means of an example. The restriction is that the network has to be two element kind, it's either LC or RC or RL. Okay, then at all poles, okay, as I said, if Z12 has a pole, it must be shared by Z22 and Z11 also. But if Z11 has a pole, it does not have to be shared by either Z22 or Z12. Does that violate the residue condition? Z11 has a pole, so K11 is non-zero. Z22, if it does not have a pole, then K22 would be 0. Z12 does not have a pole, then K12 will be 0. So it would be 0 equal to 0. It does not violate the residue condition. Now let's take an example. Let's take the same example that we took. No, let's take a different example. Suppose we have L1, L2 and C. Which parameters can we write down by inspection? Y parameters. Y11 is equal to SC plus 1 over SL1. Is that okay? Is that okay? Y12 is equal to minus 1 over, no, minus SC. Minus SC. Don't forget the negative sign. And Y22 is equal to SC plus 1 over SL2. Now you notice that the residue, the pole at S equal to infinity, the pole at S equal to infinity is common to all the three parameters. And at this pole, the residues are K11 is C, K22 is C, and K12 is, yes, K12 is minus C, and therefore minus C whole squared is C squared, and K11 multiplied by K22 minus K12 squared is exactly equal to 0. Residue condition is satisfied. On the other hand, for the pole at the origin, what is K11? Is 1 over L1, K22 is 1 over L2, and K12 is 0, and therefore this is obviously greater than or equal to 0. Okay? This is a demonstration of the residue condition. I could do this with RC or RL networks also. Any question? All right. Next we introduce a term, zero of transmission. A very obvious term, nothing very special. A zero of transmission of a two-port network is the frequency at which there is no transmission. As simple as that. Okay? A zero of transmission is a frequency at which there is no transmission, that is, the output is equal to 0. If the output is a voltage, let us say V0, then V0 at a zero of transmission, S0 shall be equal to 0. If the output is a current, the current shall be 0. Okay. Now Let's take some simple examples of zero of transmission, simple examples of network to soak the idea of zero of transmission. Suppose we have a network which can be broken up into two sub-networks connected by a capacitor. Suppose this is my total network N, which is broken up into two sub-networks N1 and N2 and the capacitor C. Obviously, at DC, because of this capacitor, there will be no transmission to N2. So, S equal to 0 is a 0 of transmission. Is that clear? Provided, there is a hitch here, provided if you measure this impedance Z in, suppose Z in is that of a pure capacitor, then what we have said is not true. Isn't that right? No, I had given this example earlier also. Yes.
If it was pure inductor,
If it was pure inductor, then also there is a 0 of transmission. There will be now two zeros at S equal to 0. If the input impedance is that of an inductor, then obviously at S equal to 0, inductor acts as a short. So the output voltage would be 0. Agreed? Now, the point that I was mentioning is, if Z in is that of a capacitor, if the input impedance is a capacitor, then obviously S equal to 0 is not a 0 of transmission. This you can very easily see. I have given this example earlier also, that if you have two capacitors in series and a voltage, let's say 2 volt, let the capacitors be identical, then you will get a 1 volt here. It is not a 0 of transmission. But on the other hand, if it is anything but a capacitor, if anything but a, let's say, resistance, then obviously S equal to 0 is a 0 of transmission. Is the point clear? Okay. Similarly, if we can break a network like this, let's say, suppose a network N can be broken up into two sub-networks N1 and N2 and connected by a shunt series resonant network, then obviously S equal to plus minus J by square root LC. At this frequency, at these two frequencies, this acts as a short circuit. If it is a short circuit, then obviously nothing will be transmitted to N2 unless, this exception must be remembered, unless the input impedance here is also a short circuit at these two frequencies. That is, unless the network looking to the right has an input impedance which is also 0 at this frequency. If it is 0, then there shall occur current division between two short circuits. Okay, current division between two. So the 0 of transmission shall not exist.
so can you please explain?
Can I please explain? Okay, suppose I have a network like this. Suppose this is L and C. This is 2L and C by 2. Okay. Now, obviously, at the frequency plus minus J by square root LC, this acts as a short, and normally nothing should have been transmitted to the rest of the network. But if by looking into the right, if you have a pair of zeros at the same frequency, then obviously this is not a 0 of transmission. That is, if you measure the voltage across C by 2, for example, you will get a voltage. Why? Because there occurs a division of current between two short circuits at the frequency S equal to plus minus J by root LC. Is the point clear? Okay. There can be many other examples of 0 of transmission. For example, if we have a network like this, L and C, then at the frequency s equal to plus minus j by square root LC, this parallel resonant circuit becomes infinite impedance, and therefore it blocks transmission to N2. So you have a zero, we have a pair of zeros of transmission at plus minus j by square root LC. Alright. Similarly, I can take examples of, let's say, RC. If there is a network N1 which has an RC series network in parallel, then there is a network N2, then the overall network has how many zeros of transmission due to R and C? No longer 2. If it was LC, then plus minus j by square root LC. Here 1 at s equal to minus 1 over RC. Correct. At this frequency, this is a short, and therefore that is a zero of transmission. Once again, that qualification should be there, that the impedance looking to the right of this should not also have a zero at the same frequency. If it does, then of course that is not correct.
So that should be S is equal to minus j over I.
Pardon me?
S is equal to minus j should also be
No j here, because this impedance is R plus 1 over SC, and this will be 0 when S equal to minus 1 by R. No j. Alright? Okay. Now, zero of transmission, depending on zero of transmission, two kinds of networks
So zeros of transmission for voltage and current are different.
may or may not be. We will come to this point a little later. Zero of transmission for voltage and current may be different, yes, may be different. But in general, let's since you raised the question, let's answer this question. In general, if Z12 has a 0, if Z12 has a 0, then Y12 also has a 0 at the same frequency. Can you prove this? If this is true, then Y12 S0 is also equal to 0. It follows very simply, because Y12 is equal to, what is the relationship? Z21 by del Z. Is there a negative sign?
Yes.
Don't forget the negative sign. So if Z21 is 0, obviously Y12 is also 0. In fact, if Z12 has a 0, all transfer functions in general have a 0. For example, suppose I want the open circuit voltage transfer function of a network, of a two-port open circuit voltage transfer function. It can be expressed in terms of Z12 and what? I have a network, I connect a voltage here V1 and I measure the voltage here V2. What is the relationship between V2 and V1?
So Z22 and Z11 and Z12.
Z21 by Z11. That is it. You write the voltage equations and put I2 equal to 0. So you get V1 equal to I1 Z11 and V2 equal to I2 Z21. I1 Z21. The ratio is simply Z21 by Z11. Therefore, if Z12 has a 0, obviously voltage transfer function shall also have a 0. Not always. There is a qualification required, which should be obvious.
Z11 is not equal to that.
That's right. Z11 should not have a 0 there. Okay. For example, let's take a simple example. Let's say an R and C in series and an R and C in shunt. This is my V1 and this is my V2. Obviously, Z12 has a 0 at S equal to minus 1 over RC. But the transfer function V2 by V1 does not have a 0 there. It is equal to 1 or half at all s. Therefore, a 0 of Z12 is not necessarily shared by all other transfer functions, but generally it is so. Unless there is cancellation, generally it is so. So it suffices to consider in ordinary cases just Z12 or just Y12. Alright? Is the point clear? Okay. The other two terms that we have already introduced, we would like to recall at this point. Do you recall what is a minimum phase transfer function?
Poles and zero left up.
Poles of any transfer function have to be in the left half plane. Have to be. They cannot be in the right half plane. So it is the zeros. Minimum phase transfer function is one in which the zeros, all transfer function zeros are zeros of transmission. Isn't that right? So minimum phase transfer function is one in which the zeros of transmission are in the open or closed left half plane. Open or closed? Closed. Are in closed left half plane. If the function has to be non-minimum phase, there must be at least one zero in the right half plane. At least one zero, at least one, it can have more. 1 0 in right half plane. Can you give me an example of a non-minimum phase transfer function? An all-pass function. First order all-pass is of this form, s minus 1 divided by s plus 1. The 0 is in the right half plane, the pole has to be in the left half plane. In addition, if you recall, all pass functions have the elegant property that yes, phase shift of course, but the property in terms of poles and zeros, they are not symmetrical. That's not the language. Mirror image symmetry. The symmetry is that of mirror image, considering the j omega axis as a plane mirror, right? J omega axis is a mirror, there is a mirror image symmetry. So minimum phase and non-minimum phase. And now we are going to state a theorem. And the theorem is that if the network is a ladder, alright, you recall what is a ladder? Okay. If the network is a ladder, then it has necessarily to be minimum phase. A ladder is minimum phase. This is the theorem. And the theorem can be proved very simply by common sense. Take a ladder. A ladder is like this. Okay, this is a typical ladder. A ladder is minimum phase. All that you require to prove is that the zero of transmission of the ladder is always in the left half plane. Poles, no question, poles have to be in the left half plane. Okay, it's only the zero of transmission. Now, how can a ladder block transmission? It is either two things can happen. Either a shunt element can be a short circuit or a series element can be an open circuit. Now, a series element open circuit means what?
Voltage.
Suppose an element Zj is an open circuit, which means that it has a pole at that frequency. Right? How can it be an open circuit? At that point, that frequency must be a pole of this impedance. Similarly, if you have a, let's say, Yk, an admittance here, let's put it as Zk, an impedance Zk, then a zero can be created by a zero of Zk, right? And a ladder has to be made up of only impedances, right? And these impedances are passive and reciprocal, and therefore the poles and zeros of these impedances are in the left half plane. Agree? Which means that the transmission zeros of a ladder must all be in the left half plane. There is no other way that a zero of transmission can be created in a ladder, right? It is either a series impedance pole, now we state it in a formal language. A ladder, the transmission zeros of a ladder are constituted by two kinds of frequencies at which the series impedances have a pole or shunt impedances have a zero. And since any driving point impedance has poles and zeros in the left half plane, the transmission zeros of a ladder must be in the left half plane. In other words, a ladder must be a minimum phase. Are you convinced?
No, sir. Can you please
Well, what I was saying is, if it is to be minimum phase, then its zeros must be in the left half plane. How can the zero be created? Either an impedance will be open, series impedance. Where can it be open? At its poles, and its poles must be in the left half plane. Or a shunt impedance can be a short circuit. Where can it be a short circuit? At a zero. Where can it have a zero? In the left half plane. And therefore all transmission zeros of a ladder must be in the left half plane. A question: can a ladder have multiple transmission zeros?
Yes, sir.
I have not finished the question. Anywhere in the S plane?
No.
Can it have a multiple?
No,
Pardon me?
sir.
Why not? Anywhere, because the zero of Zj, any impedance, can be anywhere in the left half S plane. Suppose this zero is this pole is shared by another series impedance, then there will be two zeros of transmission at the same frequency.
So again, won't there be any division of voltage or
No,
sort of stuff?
they are quite separate from each other. Let me take an example. You know this phase shifting network. Where are the zeros of transmission? Obviously at S equal to 0. At BC, if you have a voltage source here, nothing will appear here. How many zeros of transmission? At obviously 3. One due to this, one due to this, one due to this. So it can have multiple zeros of transmission at any point in the S plane. Suppose we had a resistance here, then obviously this zero would have shifted to the negative real axis. Suppose we had an L here, then identical. Then these zeros of transmission would have been complex. Alright. Therefore, it is possible for a ladder to have multiple zeros of transmission anywhere in the S plane. No, not anywhere in the S plane. In the left half plane. In the closed left half plane. Okay. Can it have multiple poles? Transfer function. Can it have multiple poles? Not on the j omega axis. It may have elsewhere. On the j omega axis, no. No transfer function can have multiple poles on the j omega axis. Okay. We'll start from here tomorrow.